In this video, we're going to talk about volume of a solid. This is the first of three parts dealing with volume. In this first video, we'll talk about general solids, and in the second and third part, we'll talk about two different ways to deal with solids of revolution. So we want to find the volume of a three-dimensional object, and we're going to start with what's the simplest figure that we can find volume of. That's what's called a right cylindrical solid. So here's an example picture. You have a plane region, so this, what I call B1 here, is two-dimensional object, something in a plane. You have a congruent region, so a copy of B1 in another plane, a parallel plane. So B1 and B2 are in parallel planes, and then you just connect corresponding points. You take a dot down here and you connect it to the same point up here, and you fill it all in and you make a solid. That's called a right cylindrical solid. The reason we start with that particular shape is because the volume is easy to see. Just in general, the base here could be any kind of shape. I've just drawn like this kind of blob. If this base happens to be a rectangle, you'll get a rectangular box. If the base is a polygon, then you get a prism. If the base is a circle, you get a circular cylinder, which in common speak is usually just called a cylinder. And if the base is like this, amoeba-shaped blob, you get something, who knows, doesn't have a name. The key fact about these right cylindrical solids is that congruent cross-sections are congruent when you cut parallel to the base. So if you take another plane somewhere between B1 and B2 that's parallel to these, cut through here, okay, take a cross section with a parallel plane, a plane that's parallel to the base, then the cross section is another copy of this base. Okay, wherever I cut, at whatever level of this solid I cut, as long as I'm staying parallel to the base, I'm going to get a copy of the base at every level along the height here. So that means the volume of this cylindrical solid is the area of the base times the height. That's it. So here's the formula. V is the volume, A is the area of the base, and H is the height. So that's the distance between these two, B1 and B2. That's it. Now, that's great if all solids were cylindrical solids, and of course they're not. So if you have something that's not this simple kind of solid, how do you find the volume of that? And the strategy is similar to what we did to find the area under a curve. That is, we cut the solid into a bunch of pieces, and if they're small enough, we'll approximate those small pieces with cylindrical solids. We'll find the volume of each of those approximations and add up all the results and give you an approximation for the whole thing. Alright, very similar to what we did with Riemann sums. We want area under a curve, so we chopped it up into a bunch of pieces. We approximate each piece with a rectangle. We added up the rectangles, and then of course to make the approximation better, you increase the number of rectangles. And we'll do the same thing here. Alright, so here's an example. If I want to find the volume of a loaf of bread, what I'm going to do, is a loaf of bread a cylindrical solid? No, because as you know, if you cut a slice of bread or a loaf of bread, these cross sections, okay, each of the face of each slice is not exactly the same. They're close, but if you take this slice here and you put it next to this slice here, they don't line up. So when you smear your peanut butter or your mayonnaise on there and you put the other slice on top, it doesn't quite cover it all up. In fact, if you just take this slice and you turn it around, it doesn't quite line up with the one next to it anymore. So they're not exactly the same, but this slice, just imagine this slice right here. If I take just this slice out, the one side of it and then the back side of it are almost the same. This is almost a cylindrical solid. Not exactly, but pretty close. So we'd estimate the volume of this slice by taking the area of one of these faces. Take this out here and measure its area, and then multiply by how thick this thing is, and that would be approximately the volume of that slice, and then we'd add it up for all the slices. Alright, so let's make that a little more mathematical. I'm going to have this solid, which I'll call S, it's going to be oriented along the x-axis between x equals a and x equals b. I'm going to divide up the interval on the x-axis from a to b into n subintervals of equal width, and I'm going to call that width of each subinterval delta x. Okay, this is the same setup we had with Riemann sums. I'm going to label the endpoints of those subintervals with subscripts, so x sub 0 will be the left side, that's a, and then x1 will be the next endpoint, x2, and so on up till x sub n will be b, the right side. Alright, so far same kind of setup we had with area under a curve. Now, we'll start doing some volume stuff. I'm going to define a function a of x, to be the area of the cross-section of the solid obtained by taking a plane that's perpendicular to the x-axis and that goes through x. Okay, so you give me an x and I take a plane that is not parallel to the x-axis now. It's going to be perpendicular to the x-axis, and it's going to go the x-axis, it's going to intersect this plane exactly at the x that you gave me. Okay, that plane is going to cross the solid S, and I'm going to take that intersection, which is some sort of plane region. Alright, it's a two-dimensional cross-section of the solid. I'm going to take that, I'm going to find the area of that two-dimensional object in the regular two-dimensional way, or however I can find that area. Okay, now I'm going to approximate the volume of the solid between x sub I and x sub I plus 1 by what I'm going to call v sub I. V sub I is the approximate volume of the ith slice. So I have a slice between x sub 0 and x sub 1. That's the 0th slice, I guess. And between x sub 1 and x sub 2 is would be the first slice, and then the second and third and so on, up until the n minus 1 slice. I'm going to take the x value from the left endpoint of that subinterval. Okay, x sub I is where the subinterval starts. I'm going to plug that into my area function, and that's going to give me the area of that cross section. I'm going to multiply by delta x. Delta x is the width of the subinterval, so that's the width of each slice. So in other words, I'm going to treat the portion of the solid between x sub I and x sub I plus 1 as a cylindrical solid where the base is whatever the cross section is at x sub I and the height is delta x. Okay, add up all of those approximations and that will give you an approximation for the volume of the entire solid S. Now, this is a Riemann sum. A Riemann sum is a sum of a function evaluated at some point within the subintervals multiplied by the width of the subintervals. So this is a Riemann sum. When I take the limit as n goes to infinity, I get an integral, and I also get a better and better approximation, so I'll get the actual volumes. I'm going to define the volume of a solid to be the integral from a to b of this a function, where a is the cross-sectional area. The hard part about this process is finding this a function. What is the area of a cross-section? Okay, well, let's apply this idea to find the volume of a sphere of radius r. Now, you might remember the answer from geometry. You don't need calculus to do this. You can use geometry and figure out this volume, but let's see that calculus gives us the same answer. So, I'm going to put the center of the sphere at the origin. So here's my sphere, and right here in the center is the origin, 0, 0, 0. Okay, I'm in 3 dimensions now. On the x-axis is going to go this direction, left and right. The sphere is going to start at negative r, so that's this side right here, where the x-axis crosses the sphere at this side. That's going to be negative r. Okay, the sphere's radius r, so negative r to 0 is r. And then from 0 to r, so this side will be r. So this goes from negative r to r. If I take a cross-section perpendicular to the x-axis, that's what I'm trying to draw here with this. Okay, the x-axis is going left and right, so if I cut perpendicular to that, I get something that's in the yz plane. And that cross-section is a circle. The radius of that circle is the distance between the x-axis and the top of the circle, which is the y value of this point. Okay, right here at the very top of this cross section, right above the x-axis, so z coordinate 0, this is whatever the x coordinate is where I've cut, and then the y coordinate gives you the height of this circle, and that's the radius. So the radius here is y. If this point right here at the top of the cross section is xy0, then y is the radius. Okay, I need the area of the cross section as a function of x, not y. So I need to figure out a relationship between x and y. And, well, the relationship between x and y is that this is a point on the sphere. So here's the equation of the sphere. X squared plus y squared plus z squared equals r squared. So this is the particular point I'm looking at. I'm given an x where I took the cross section. I want to figure out what y is. Z is 0 because I'm right on the very top of that circle, right above the x-axis. So z is 0, so you get this thing. Solve for y, and you get this. I'm going to just take y's positive, okay, the one on top of the circle, rather than the one on bottom. Okay, you get negative y down here. Would also be a solution to this equation, would be this one. But I don't care, I don't want that one. I want the positive one to give me the radius. Okay, so this is the y value of that point. That is the radius of the circle, that's the cross section. So the area of a circle is pi times radius squared. The radius is y. Y is equal to that. I just solved that. And so I get the area of the cross section at x is pi times r squared minus x squared. So the volume of the sphere is the integral from minus r to r. Remember, x ranges from minus r on this side to r on this side of the area function. Area is a function of x, which I just figured out is this formula, so that's it. And this is not that bad of integral. Remember, r here is a constant, so pi times r squared is just we're integrating a constant and from minus r to r. And this is, you know, just a quadratic, so no big deal. But I'll have Sage do it anyway. So here's my integral command. Don't forget to declare the variable r before you do this integral. And pi times r squared minus x squared. The variable of integration is x. X ranges from minus r to r, and the answer is 4/3 pi r cubed. There it is. That's exactly the same answer we learned in geometry. So that's good. Calculus agrees with geometry. All right, third example. I'm going to look at a pyramid, right? A right pyramid, so one that goes straight up and down, doesn't slant. I mean the vertex here is right above the center of the base. Make a right pyramid. The base of this pyramid is going to be a square with sides of length 10. So this is a 10 by 10 square. The height is 5. Okay, so this picture is not drawn to scale because this the base is supposed to be 10, and this height here is 5. I've kind of stretched out the height longer than it should be, just so I can see inside the pyramid at this little cross section better. Now, why I decided to draw this sphere in black and the cross section in blue, and here I drew the pyramid in blue and the cross section in black. I have no idea why I changed the way I did the colors, but oh well, that's okay. Put the vertex of the pyramid at the origin. Okay, I'm actually going to turn the pyramid on the side. It's going to be convenient to do it that way, since I define my volume in terms of area of cross sections along the x-axis. So it's going to be convenient to cut the pyramid this way. So I'm going to put my vertex of the pyramid right at the origin. I'm going to have the x-axis go right down the center. So hard to do this in 2 dimensions, so I just drew this with straight lines in 2 dimensions. You got to imagine this x-axis here sticks it right out of the center of this square. So anyway, imagine that. The solid then, in terms of the x-axis, it goes from x equals 0 right here at the origin until x equals 5. That's where this end is. Remember, that's the height 5. The things on the side, so the height is the distance here. So from 0 to 5 is where this is along the x-axis. If you give me an x value, I'm going to take a cross section perpendicular to the x-axis. Okay, that's here, like for example, this little black square. Okay, this cross section is going to be another square. If it's going to be perpendicular to the x-axis, that's going to make it parallel to the base, and so you're going to get another square. Not the same size square, it's a smaller square, as these sides slope down here to the vertex, the square is smaller. So the area of this cross section is just whatever the side of this square is. It's going to be s times s squared. The key here is to figure out, well, how long is this side in terms of x? Okay, x, remember, is the distance from the vertex down to here, and I need to know how long this side is. Okay, so there's different ways to do this. One way is to use similar triangles, and that's probably the simplest way if you understand and remember similar triangles from geometry. In my experience, a lot of calculus students don't remember lots of geometry, so instead of doing this the geometry way with similar triangles, I'm going to go ahead and do this the algebra way and look at the equation of the line that connects this point here, the vertex, with the point here on the square. This line goes right over the side. So let me cut this pyramid the other direction, right along the x-axis. Okay, I'm going to eliminate z. Take z equals 0 and just look at the xy plane. So I'm going to have the x-axis goes right through here, and I'm just going to cut it now parallel to the, let's see which one. Well, take the xy plane and intersect it with the pyramid. Okay, so this is what we get. Pyramid laying on its side. And the rest of the pyramid, sticks out of the page, sticks into the page in the z direction. Okay, so here's the vertex 0, 0. The top of this pyramid is 5, 5. Why? Well, the x is 5 because that's the height. What about y? Remember, the x-axis goes right through the middle of this square. And it doesn't look quite like it because I didn't draw it perfectly, but imagine this goes right through the middle. That total distance from bottom to top is 10. So if you're right through the x-axis right through the middle, it's 5 up and 5 down is what gives you 10 total. So this is 5, 5. This is 5, negative 5 down here. This is the cross section. In the cross section, the x value is x. What's the y value? Well, what we wanted to see up here is that this is exactly the line y equals x. Because it goes through 0, 0 and 5, 5, this is the line y equals x. So if I take the cross section at x value x, the y value is also x. Y equals x. That means the length of this side. Okay, remember, this is a square. This is just this is the middle of the square, and you got to imagine that sticking out of the screen and sticking into the screen is the rest of the square. But this total distance here from negative x to x is the length of the side. That's what I call s up here. So s is 2 times x. X here and x there. And so 2x is the length of my side. So just like here, at 5, the length is 10 because the base is 10 at height 5. At the vertex, it's just 0. So, and so all the way through here, if I take a cross section here at 2, then the length of the square I get there, my cross section will be 4, and so on. So my area function, the area of the square is the side of the square squared, and we saw that s is 2x, so we get 2x squared, and so we got 4 times x squared. I'm going to integrate that from 0 to 5 because x ranges from 0 to 5. The answer, I had Sage do it, though again this is not a hard integral to do yourself, is 500 thirds. And if you look up the formula for a pyramid from geometry, you would see that that does agree. Okay, here's one that's not a simple figure that you learned about in geometry. So I have a solid whose base is this ellipse. Okay, I got an elliptical region with boundary curve 9x squared plus 4y squared equals 36. That's what I'm looking at right here. Here's my ellipse. Imagine this is all filled in. That's the base of the solid. And cross sections perpendicular to the x-axis. Okay, so if I take a cut this way, here's the x-axis along the bottom, left to right. If I take a cut this way, all right, you got to imagine the solid, this is the base here on the screen, so the solid sticks out of the screen. When you take a cross section perpendicular to the x-axis, okay, I cut this way, and I look at it, what I see is an isosceles right triangle whose hypotenuse is in the base. Okay, so I cut here. This is the hypotenuse of the triangle, and sticking out of the screen is an isosceles right triangle. Okay, the right angle is going to be up at the peak. So imagine a triangle sticking out of the screen, and if you touch the point that's closest to you, sticking out of the screen, that's where the right angle is. And the two sides going out from that are the same. It's an isosceles right triangle, and then the hypotenuse of that triangle is in the base here. Okay, well, I don't know what that solid looks like. I have trouble imagining it. Let's just say that that's what it is. Such a thing is possible. All right, whoops. Cross-section perpendicular to the x-axis through some point xy with y greater than 0 on the ellipse is an isosceles right triangle. Okay, so I'm going to take, you give me some x value. I'm going to take my cross-section. Let's say x is right here. I'm going to look at the point at the top of that cross-section that's in the base. It has x value, whatever x you gave me. The y value is some y greater than 0. Okay, I'm not going to take this one down here that has the opposite of that. That'd be the negative y. I'm going to take a positive y right here. So this is the point xy, where my cross-section borders the base here. Okay, that cross-section is an isosceles right triangle. The hypotenuse is in the base. So what's the length of that hypotenuse? It's the distance from this point xy down to here, which is x minus y. Okay, this is symmetric, so same distance below the x-axis. Well, the x-axis goes right through here in the middle. Sorry, got this frame here instead of the axis drawn. So the x-axis is right through the middle here, and so this is xy, this is x minus y, so the distance there is 2y. So 2y is the length of the hypotenuse. Okay, then you have two legs. I'm going to call the length of the legs s. They're the same because I told you it's an isosceles triangle. I need some connection between s and y. So that comes from the Pythagorean theorem because it's a right triangle. So if I square these lengths of the two legs and add those together, I get the square of the length of the hypotenuse. So s squared plus s squared is 2y all squared. Or in other words, 2s squared is 4 times y squared. Now, what I really want is a relationship between s and x. Why? Because I want the area of this triangle. And the area is, well, the area is 1/2 base times height. The base and height are the same. Okay, the two legs are the same. So imagine this is a right triangle. Take it out, sit it down. You have one length s along the base. You got another one along the height, and so they're both s. B and h are both s. So that means the area is 1/2 s squared. I want the area as a function of x. Okay, if I'm going to do volume, I need to integrate with respect to x. And so I need a cross-sectional area in terms of x. So I want to convert this area from s to x. That's why I'm doing up here. So here's 2s squared is 4y squared. The next one comes straight from the equation of the ellipse. 4y squared is 36 minus 9x squared. Just subtract 9x squared from both sides and you get 4y squared. We don't even have to solve for y or anything. We want 4y squared, and we got 4y squared is just subtract 9x squared from both sides. So 2s squared is that. What I want is 1/2 s squared. So how do I get from 2s squared to 1/2 s squared? Well, I got to multiply by 1/4. So if I multiply this equation by 1/4, I get 2/4, which is 1/2 s squared. And over here, I get 1/4 times this quantity. So 1/2 s squared is 1/4. 36 minus 9x squared. That is the area of my cross-section at x. That's what I want to integrate. From -2 to 2, integrate the area function with respect to x. The answer turns out to be 24. So that is the volume of that crazy-looking solid, whatever it looks like. Now, this is a very common strategy we see here. You have a complicated problem, break it up into small pieces, approximate the answer for those small pieces using something easy, combine all those approximations and get an approximation for the total thing, and then increase the number of pieces. Make the pieces smaller the approximations become better, and basically you take the limit as the number of pieces goes to infinity. There's many examples where that kind of strategy results in an integral. We've seen two at least. One is area under a curve, which we did with Riemann sums. The second one is this volume. We're going to see several more as we go on. There'll be arc length and surface area and work, a number of applications, and there's many more that we won't cover. Next time we'll return to volume again. We'll look at solids of revolution. So that means you take a function usually, and you look at the area under the function in 2 dimensions, and then you rotate that around either the x-axis or the y-axis. So you rotate a 2-dimensional region around an axis, and you create a solid called the solid of revolution. And we're going to look at the volumes of those. And since the cross-section is a circle in that case, then it's easier to find the volume. It's not quite so much crazy algebra like we had up here. But we'll do that next time.